Today I want to talk about T equals W. And just to sort of lead up to that, we have this algebras is colon branches, but we shouldn't think about algebras. Don't usually have physical meaning, right? They are functions on something, but the points on that something have a meaning, and those correspond to the representations of the algebras. We should think about algebras in terms of the actions on something interesting. And so what do colon branches act on? And they, I think that's the whole idea, is that they're supposed to, so first we want to construct an action, also we want to globalize to get something more geometric, because it's a fine Grassmannian is something strange. It's not, but something geometric is something like moduli space of bundles and something like that. So that's why we want to do this moduli space. So we fix the sigma. This is a algebraic curve minus G, and this may be K 5 points. And then we fix also rank and degree, and we look at this Higgs. I don't know, sigma R and D. This is a. So let's start with just some abstract, but we will be more complete later. Moduli stack of Higgs bundles. Sigma. So, what is this? This is collections of E and theta, where E is a vector bundle on sigma of rank degree RD, and theta is, so in the simplest situation with no marked points, it is what you usually have. It will be just this, but with marked points, you also allow here the you divide, you twist by the divisor D, where D is encoded in the K marked points. So this is very large, and it's not symplectic. That's a warning. But to get some actual varieties, we need to introduce stability condition and fix some other thing. So there is so-called the hypercamp parameters. And you, for each M S in the divisor, you need to pick the this is T R and T C. So this lies in R to the R, the rank, and this lives in the C, the rank. And then once we have that, we can define, so using TR, we define slope of any Higgs bundle, parabolic Higgs bundle. Which is simply this is simply degree of a rank if D is empty. And then this gives us a notion of stability. So we can get a stack of stable Higgs bundles inside all of them. Well, I have to put D here in notation, but it's a bit ugly. Yeah. I'm sorry. I put on here. And D. And this is open. And then there is a map to. So there is a map to see. Well, even from here there is a map, but we look at CR times the size of D. So reading off the. All right. Yeah. I forgot to say. Yeah. Sorry. This is my. So. Yeah. Right. So here we also need flags. Yes. Flags at marked points. And this has to respect the residue of theta in each point X, where X in D. Residue has to preserve the flag. That's the problem with parabolic bundles. It's just too much notation, and then you kind of forget about what you want to do. Right. So
the parabolic means that the flag is partial.
So I work with complete flags, but you can of course complete flags in every puncture. Right, and then the residue, since it is a differential form with simple pole, this notation means that, and this is matrix valued differential form, simple pole at X, and that you can take the residue.
Sometimes there's a condition that theta wedge theta is 0. You don't ask this.
Right. So that's right. So this is I think maybe it is a analogy of the moment map. Maybe it is a moment, but so this map reads off the eigenvalues. This map reads eigenvalues of this residue theta for each in the divider. So you get R numbers for each point of the divisor. Because you have a complete flag that give and the residue is upper triangular, you just take the diagonal. And then so they're saying that this thing is not symplectic, but the fibers of this are symplectic. So these are the symplectic leaves of this big thing. The fiber. Okay. So if so, unless see so, unless this parameters, so you have this things belong to some exceptional codimension 3 walls. The fibers are actually smooth and symplectic varieties. They're actually hyperkähler, but I never studied this properly, so yeah. Okay, this is clear.
Would you remind where TR comes from?
TR is a stability. It defines the slope. You have
the slope.
to stability to say something is stable. You always say that for any sub-object, the slope should be less than that. That's the slope. To define it, there's parameters TR. Okay, maybe. So there are these flags, right? And if you have a sub-bundle, it will intersect this flag in some steps. And the better it intersects the flag, the more is the slope. And so for instance, line bundle can be contained completely in pass through the smallest step in the flag. That's kind of make it very, very, very exceptional somehow, right? And so the slope should be higher. And the weight of that thing is counted with the corresponding. I don't know. For me, Simpson, for instance, Simpson's papers. Okay, that's
Sorry, you nodded and said yes, but you didn't answer the question. Is there a condition about theta wedge theta? Like
about what?
theta wedge theta?
It's on the curve.
Oh.
So algebra.
Hold on, sorry.
Yeah. Right. So you have this this moduli space, and the meaning of the Coulomb branch is that, so recall that branch there is this spec of the K theory or homology of a Raviolo, and Raviolo is a what is on the disk. It is a it parameterizes pairs of Higgs bundles on the disk, as it was given in Professor Nakajima's talk. There was cotangent to R, and that R should be thought of as a moduli stack of Higgs bundles on the disk. And so you should use it to define modifications of Higgs bundles. So you have here's modification, how it works. Hecke modifications. You have some Higgs bundle. I don't know, eta on so E theta and the flags, and so on some big global surface, and you have some point, and you cut it out, and on that point you have some Higgs bundle on the disk, right? On that point, you are supposed to cut it out and then plug in the other Higgs bundle, which lives on the other side of the Raviolo. You cut it away and use put in the second Higgs bundle. That's so out of this you should you expect, I think this was it in Jouet-Yun's papers that you prove that this acts on the cohomology of the like on the moduli space, or
Stability condition might not preserve it.
yes, there are problems to deal with expected, but let's write it expected to act. So that the corresponding Coulomb branch. sorry, not Raviolo, but bundles on Raviolo moduli space. So Coulomb branch functions on Coulomb branch expected to act on the cohomology of I don't know different on stable moduli space.
I'm sorry, you're talking specifically about Coulomb branch of the Jordan quiver.
Yeah. Right. Okay, so that's how we logically arrive to somehow what I'm going to speak about. So so now what about the concrete application? Equals W, and so so in the case of no parabolic points. Was given formulated by Hauser, Verini. This is P equals W conjecture. So we have this moduli space. This is called this is called the Dolbeault moduli space. Is denoted. And on the other hand, there is a non-abelian Hodge correspondence. To the sort of Beatty moduli space. And this is this just space parameterizing sort of matrix tuples of matrices, total monodromy matrices. Connections. So up to conjugation. So this is related to the Deligne-Simpson problem as yesterday debate talk. So to define everything properly, and especially in the parabolic case, you have some strange thing. So you want to look at, so you have your surface, and you take I1 of the surface minus the divisor. This set, this tuples of matrices basically maps from the monodromy, from the fundamental group to GL and C, satisfying then there is a procedure that tells you how to convert those parameters. There is some stability. Some other, so with respect to real part. C. And imagine it doesn't matter. Okay, and that, yeah, also flux. stability with respect to this, and then requirement that monodromy around point X in D. You fix a local monodromy. It's supposed to be conjugate to the matrix exponential TR plus. Sorry, so real part of C plus 2 pi, right? But there's some complicated transformation parameters, but in the end parameters all match. And and the fact of this non-abelian Hodge theory is that MB is diffeomorphic to the M Delvaux. As topological as manifolds or as topological spaces. And then there is this picture that was in Jouet's talk that you there is a you can think about a family of parameterized of lambda connections, and although that picture is working for this space. Right. And then these people they studied the cohomology ring of this space, of this topological space, and they study how the cohomology ring acquires extra structures on two sides, and they want to match the structures. That's the content of the lecture. So on homology ring of this topological space, we have first thing is a weight filtration. From MB. So this is a algebraic variety, so its cohomology, it's smooth. Its cohomology has a weight filtration, which turned out to be like this mixed Hodge structure. Structure is Tate, what's called Tate, which means that only HPP non-zero. And that's sort of, and you use the weight filtration. So I'll call it WI. Then another thing is that this M Delvaux, it's fibers over the Hitchin base. And with the C to the dimension, half the dimension of the space. And this is completely integrable system, and that's makes it interesting. But from the point of view of algebraic geometry, this implies that the cohomology of this space is a decomposition. So sorry, so this is proper. This is Hitchin map. And so which implies that the cohomology has a natural filtration, perverse filtration. And the conjecture is that the statement is that pi equals w2i. This is up to certain translation. In the definition, there are different conventions, and if I didn't specify the convention, then I can play it this way. But so translation. That's what we what was conjectured, and so in September last year, we have two proofs. One was by Mellit and Shen, and this involves some support theorem, and it's refined kind of support theorems, let's say. Theorems. So it's actually dealing with perverse sheaves, and well, I'm not going to go into because so right after they upload the paper, we uploaded in like in a few days paper by just also me, and then Sasha Minets and Schiffman. Using the algebra actions. On cohomology. And this is what I will talk about. So which, right, so let's see. Here behind the proof, and to explain. So first I have to explain tautological classes. So this is a fact that the cohomology of this this cohomology ring is generated is a polynomial ring in some generators, which I will call them. I will denote them like this: psi k, right? Model some relations. So all we care about is the relations after we write this. And this, so what is this psi k? Psi k, psi. So we need to look at the this is the tautological bundle. So it's bundle on the, let's say in this realization Delbo, we have this. So it's a very point of this space. We have a Higgs bundle on the surface. And we take the Chern character of this, and we what is psi? Psi is an element in the cohomology ring. Is cohomology of the Riemann surface, and we cap it with psi. And to make it more interesting, this formula simplifies the formulas a bit. You cap it with a third class. And then you have this cohomology class living here. And I'm going to project it to the space and using that, because this is compact, so there's a proper push forward. And then and then I get a series of cohomology classes. And then I would take the sum psi k psi over k factorial. Yeah.
Are you making a K theory calculation here?
It's equivalent to K theory calculation.
Seems like Riemann rock, you're capping on.
Yeah, sure. Yeah, of course. It would be, I could do the same in K theory.
Which would be the natural.
The conjecture is for in cohomology, so get something in cohomology.
So with K theory, you wouldn't have the Todd, what I'm saying.
Yeah. Yeah, so I write it like this, and then this class lives in the cohomology degree K minus 2 plus pi of the model. Okay, that's logical classes, and then there is another fact. This is related usually as Schender's result for the non-parabolic case. Then for the parabolic case, I wrote it, and so the weight filtration is completely determined by this presentation. That's what I want to say. So the weight WM, Sam is a span of the products like 1 psi km psi kr L psi L, where the condition is that sum of ki's is twice the sum of ki's. Let's recall them. That's basically the statement. So from this point of view, weight filtration is simple. Okay. Yes.
For weight filtration on the Betty space, right? And
Yes.
It's Higgs bound, so it's still both.
Oh yeah, yeah. No, this is topological construction. You can do it. This is a complex bundle. Its structure group is complex, but it doesn't matter if it's holomorphic or not. You can do it. Besides, I mixed it up, but doesn't work. Okay. So. Yeah.
Would you comment in this formula where you have a sum with k factorial? What's the role of k? How do you decompose?
According so that this holds. According to degrees. So now the more some idea, okay, is that so there are classes. So for instance, on one side we can consider classes psi k over point class. So point is a class in H2 of the curve. So what does these classes do? Say you take this point And you have a vector space. So you have if you have a Higgs bundle over a point, you get a vector space, and this simply measures the Chern classes of that. Of this bundle at that point. Any point, they're all the same Chern classes. And so it's sufficient to consider. I mean, you can instead take CK instead, for instance. These are just polynomial transformations from one to another. That takes the Chern classes, Chern classes, these are Chern characters. Take those, they're finding only K of them, right? And they correspond to the fundamental representations of your GNN. On the other hand, like in Alex's talk, there are these monopole operators, which are parameterized by, well, also fundamental representation of dual group and some extra data, but they are very intuitively, they're very, very easy. Remember the last time. So on the other hand, we have like monopole operators. And in my diagrammatic language that I introduced, you have this line of thickness n corresponding to the fiber of your bundle. Then you split off line of thickness k. You can go back here and merge it back like this. This what the pictures for the monopole operators. If you want some putting decorations here, I mean putting the cohomology of the Riemannian. But if let's just don't put anything. This is the picture, and what corresponds to you have this bundle, and you have a choice of you choose a subspace of the fiber, and say that it is invariant under the theta. Then you can modify the bundle. You can consider new bundle whose sections have simple poles passing through U. The construction of new bundle. So use this idea, you get the correspondence, and then if all the stability problems are solved, then you get a map action on the cosmology. But just to explain the idea, we should think about this to be somehow dual to each other. And we want to kind of find this duality explicitly. So I don't know, compute algebra generated by this, and then find some transformation. But it's a non-trivial thing already. If I say, if you have some relation between these classes here, you can ask, do we have the same relation between these operators? And that's idea. I don't know. Is this in Witten or some? I don't know. Some, because these are called the Hooft operators, and these are called the Wilson operators. Yeah. So anyhow,
Sorry, in your picture, did you change the rank of your main bundle as this thing split off?
No. it didn't. No. Yeah. I. Okay, so now let's go to the. So what can we do about this? So this idea also should be also globalized to all psi k psi on this side in some global Hecke operations. This side. And so for technical reasons, we have to restrict to easier, nicer moduli space. Call it, let's write it like this, and nice is sitting inside the M dot ball. It's open. And this nice moduli space is like in Roman stock. This corresponds to the condition. There is a spectral curve given by the eigenvalues of theta inside the cotangent bundle, twisted cotangent bundle. Sigma. And we are defined by condition that spectral curve is irreducible. Moreover, residues of theta at x for in t has distinct eigenvalues. So this space is much is open, right? You may think that you lost a lot by getting to this space, but it turns out that so fact position and the restriction on the cohomology is injective.
It's open in the risky topology.
Yeah. And that also means, so this also is known to be pure. And so this identifies us as with a pure part in the cohomology of this model space. So this cohomology group is identified with a pure part of the cohomology of this nice open part, and also corresponds to the image, the subring generated by tautological classes of this nice moduli space. That means this is a subring generated by tautological classes. Okay. So another sort of fact will be that this and respects perverse filtration, respecting perverse. Okay. So on this moduli space, there is no problem in the definition of Hecke operators because stability conditions are always satisfied. It's because if you have a subbundle of a Higgs bundle, its spectral curve has to be an irreducible component of the spectral curve for the ambient bundle. And if you impose this condition, then There is no, it's not possible. So you don't, stability condition is trivial, is void, always satisfied. And so we can define certain Hecke operators, which are indexed by T psi. They correspond to actually the first fundamental representation, monopole operator, or fundamental representation, and so using explicit correspondence, we can compute their action. There is an algorithm to compute them on the tautological ring. And then we verify that from this proposition, the distance on direct sum of homology ring over D of some parameter U. We have an action. This is nice and tautological ring with an action of the Lie algebra with basis P and N psi, so that psi K psi P 0 N psi P K psi T1 N psi and the commutation is particularly simple. Because the determinant of the parameters of the indices n minus m prime T m plus n prime plus n prime minus 1. So this very simple algebra. This is undeformed. Trigonometric algebra. Standard by the ring of the curve, so weighted by the ring. Okay, so now what can we do with this? You see that, for instance, let's ask, do we have that symmetry that we were looking for? And that it turns out not quite, right? Because so the psi's live on the vertical axis. On the horizontal axis, we have the operators T M0. Right? They have two commutative subalgebras, but they are not symmetric. The picture is not symmetric, and it corresponds to T times T, so or C times star. So this is actually the Lie algebra of Poisson of functions on these spaces with respect to Poisson product. So this is functions on this with Poisson functions on. Yeah, so here you need sorry, C times star. But kind of you can relate it to T times T. And this is not symmetric. So let's use our imagination. How can we make it symmetric? One way, what Newton would probably like is he would suggest to pass to the K theory. And that would make this C in C star. And then we will have SL2Z action. In particular, S matrix will change one into another. So to make symmetry, to make it symmetric, approach one and go to replace cohomology by K theory, which would replace C star. And yeah, so here the correspondence between C and C star is the exponential map because we have the Chern character, and it is infinite series, which it's sum of exponentials of the Chern roots. This map is exponential, connecting the two. But this we don't do, and I think Neg would trying to do this, or I don't know. Let's see. But we do something else. Approach two is to try to degenerate C star into C. And that we can do by some sort of strange formal procedure, which we don't quite understand. So we kind of do formally. But the meaning of that is that, roughly speaking, just to give you an idea, the operators T, M, N, psi are written as a sum of the some other operators D, M, N, psi, N prime over N prime factorial. But now N prime has to be to the power. So N is a N to the power N prime. So it is very natural if you think about connection between K theory and cohomology. It's just trying to do the same thing, but backwards in using this strange algebra of monopole operators. But it works. And so
It sums over N prime.
N prime, yes. Yeah. You see, it's like treating N as a variable. The degree. This N, the meaning. Oh, you did.
M and N, can you remember?
It's I mixed it up. M prime. The meaning of M is it changes the degree of the bundle. But now we have to treat it as a parameter and can make the degree complex number.
You say what's the meaning of N?
N is a cohomological degree. Okay. Right. So if you want to pass to K theory, you will do the same, but using the other direction, the cohomological gradient. And so we obtain the theorem. It's probably the worst saying the main theorem is it on homology ring of the tautological ring of this moduli space. Nice And then is U, and then there is V. We have to put 2 new. Somehow V corresponds to this N. We have an action. Action of the Lie algebra. With basis D and N psi, so that psi A of psi is still D okay, and D M M psi D M prime and prime prime commutator is M prime N minus prime, same like before, and then D with respect to both variables, both indices, we have -1. Yeah. So now this is Hamiltonian vector fields of C times C. And that is already symmetric. The two algebras, this one and this one, are symmetric. And there is a particular explicit way to realize this symmetry using SL2, Lie algebra SL2 triple. This contains E is psi 2 of 1. F is some 0, D2 0, 1, and H is D11 1, which we don't understand. This operator is just formal operators, but they are there and defined in terms of some procedure. And then P equals W follows from and the P filtration comes from the grading induced by the H operator. Filtration associated with the grading by H. So in particular, if you commute H with any psi using these commutation rules, you can check that it increases perversity by the number of bits. And that's it. So I just want to make maybe one last. So this for some reason we really need this degeneration procedure. I tried to use Padera Nakajima's way to relate trigonometry and rational algebras, but it doesn't work. It's just somehow completely different way. If you want conceptually, the you have Padera Nakajima. You have C2, and the form is dx dy, and this relates to C star times C with the form dx over x dy. And this is given by a map sending y to y over x. You can check formally it works. It gives you a way to embed this symplectic variety into this symplectic variety. But that's the wrong one. Somehow it doesn't work, it doesn't act on our picture, and so we need the map which sends exponential. Okay, so let's stop here.